Now, the best part about CGI is, to me, I believe that it bridges the gap between teaching learning procedures and learning concepts. CGI combines these two very important components of mathematics education and allows us to teach them concurrently and for students to learn about them at the same time, especially in concrete problem solving situations. And one of the other best parts about CGI is that it highlights some of the most important standards. And I hope that everybody has heard of this standard in the Common Core standards. I don't know how many people are using the Common Core, and that's okay. But this is one of the most important ideas to focus on in our math curriculum. And I know a lot of people sort of focus on the problem types when it comes to CGI, and those are very important. Those are connected to specific content that one would teach in an elementary classroom. But this presentation is going to focus on this much more broad standard, making sense of problems and persevere in solving them, which CGI also addresses. Now, I'd like to talk a little bit about cognitively guided instruction specifically, just to bring up some important parts that I'd like to highlight. The conceptual basis for CGI is these four major themes. The most important is that knowledge is connected. It's a rich network of interconnections rather than a discrete, isolated pieces of information, as well as knowledge being generative. That means that students use these connections to generate solutions to problems. As well, after students have generated their solutions, students describe, explain, and justify their thinking. This means that they have to express their knowledge by explaining what they thought about their solution. All along, they're developing an identity as a sense-making mathematical thinker. And that is these are the four of the most important themes for CGI besides the problem types. Now let's get back to this quote, "My kids can't do that." And so now what we know of language disorders and what we know of the conceptual basis for CGI, I would imagine that more than just a few of you are thinking, my kids can't do that, especially if you're teaching students with significant cognitive delays. I would imagine that even if you're not saying it, some of you are thinking it. What I'd like to do is turn most of your thinking to be like this teacher who was quoted in Children's Mathematics. "I teach students with disabilities in a self-contained classroom. When asked, does CGI work well with kids who have disabilities? My answer is yes." I'd like to turn most of your thinking, most of your expectations from thinking that your students can't do something or can't work with CGI in your classroom to this answer of yes. This quote from Children's Mathematics is particularly pertinent, in my opinion. The goal that students describe and explain their mathematical thinking is often presumed to be beyond the capabilities of many students. That has not been the case in our experience with CGI classrooms. The key word in this quote is presumed. Most teachers that think that CGI can't be applicable in their classroom presume that it's beyond the capabilities of their students. And when we're thinking about the word presumed, presuming competence is one of the tenets of the disability rights movement. It was born out of the work done with people who were once considered nonverbal and were thought to not have the cognitive capabilities that came with expressive communication. Though the proliferation of assistive technologies such as communication devices. This was proven to be false because people with who are considered nonverbal are, get accepted to colleges, write papers, and even write studies that this idea of presuming competence is based on. So this idea of presuming competence was written by one researcher at Syracuse University and also a person considered nonverbal who worked with that researcher. Now, how do we do this? This is a very important question. How do we integrate such rich, complex instruction into our classrooms with students who have the most needs or have the most expressive language and communication needs? Consistent routines and supports have been shown to help teachers integrate these kinds of pedagogical philosophies into their classrooms. And so I'm going to go through some of the supports that we've used in our school and that we have integrated in order to create a kind of more rich and equitable mathematical experience for our students. So I want to talk about these kinds of routines and supports. The first one is realia. Realia is another way of saying real objects used during instruction, and it makes problem-solving situations more concrete and can be connected to previous knowledge. So in this picture, you can see students working on a CGI problem, and the problem involves cutting up candy bars to give to 4 students. So 3 candy bars are shared equally among 4 students. And so we gave them real candy bars, and you better believe that there was some motivation to solve this problem because they wanted to eat those candy bars at the end. But they had to work through the problem first to make sure that everybody got an equitable share. One of our favorite ways to incorporate realia into our classrooms with a CGI perspective is through the routine counting collections. Counting collections you can read about in work by Megan Franke and others at UCLA. Gives students the opportunity to count and develop their own counting strategies in an informal situation of counting collections. So you can see in this picture, the student is counting a collection of chips, that there are different kinds of chips, so she can sort them in different ways that she can make sense of. And we have a school store at our school. So this student is actually doing work for that school store by counting the inventory we have of our chips. Now, we could ask her to count different buckets. We could ask her to count the Doritos. We could ask her to count the Cheetos. But instead, we asked her to count all of the chips and for her to make sense of this inventory in her own way. So now I'm going to show you a series of pictures of a student counting coins, and I'd like you to think about the kinds of partial knowledge that this student demonstrates that we can use to help better inform our instruction. At the CGI conference this year, Megan Franke did a session where she implored teachers to move away from the idea of mastery and to really focus on the partial understandings that students were displaying. And if we look for partial understandings, what the student does know, that can turn our classrooms from an all or nothing venture, either they mastered it or they didn't, they got it right or they didn't, into a classroom where students have all kinds of different strengths, and we can leverage those strengths in our further instruction. So I'm going to set the scene for you. This student was working at our school's coffee cart, which goes around and sells coffee and snacks to teachers throughout the day. And when you have your coffee, so I would usually get a coffee with my mug because I'm environmentally friendly. And so when I got a coffee with a mug, the price was 50 cents. And so being the annoying math teacher that I am, I would never just give the student 2 quarters, which would be the easiest way for him to get 50 cents, the most efficient way. Instead, I would dump out a set of coins and allow him to find the 50 cents on his own. So this day I dumped out some coins that you see on the table, and I'd like you to think about what partial understandings this student is demonstrating in order to inform how we would move forward with this student and with the class. So I'm gonna cycle through some slides, and I would like you to turn and talk to the person next to you or comment in the comment section what partial understandings you're seeing. So now I'm going to cycle through them again so that everybody can see them one more time. So again, this student is counting a collection of coins, and as you can see, they're not all pennies. And I'd like you to think again about the partial understandings that the student is demonstrating. Partial understandings the student is demonstrating. Some of the ones I'd like to point out are that this student is not just counting by ones, and he has one-to-one correspondence because he's making groups. So the student has the beginnings of some multiplicative thinking because he's not just counting by ones, he's not adding them all together, but he's making groups. But as you can see, there's a dime on top of the pile of pennies. So he's not making groups independently yet, but he's demonstrating partial understanding of making groups. Here's a close-up of his groups. And so you can see he's on his way. And I'll tell you that he's making groups of 10 pennies. So that group that's already made with the dime on top is actually a group of 10 pennies with the dime on top. So he continues to make groups of 10 pennies until he realizes that he needs to take the dime off of one of the groups so that he can get 50 cents. So he has groups of 10 pennies in order to get 50 cents. So he has 4 groups of 10 pennies and 1 dime. And so he has partial understanding of making groups, and he also has partial understanding of the equivalence of different types of coins. That 10 pennies equals 1 dime. Another support that we integrate are visual cues and color-coded annotations. Now, I want to spend a second explaining the difference between visual cues and pictures. So most people who want to integrate visuals into their problem solving will just put a picture that they think will help students make sense of the problem. And that's good in one aspect, but what you want to think about adding visuals to any kind of problem solving worksheet is how the student is going to interact with that visual. Is this visual going to lead them to a misconception? Is it going to be used as a tool for them to make sense of the problem and then help them solve it? So this student is interacting with the candy bar problem, and he's demonstrating